I'm George Jenkinson. I'll talk through our paper Coil-Tac, a coiled capacitor mechanism with liquid metal for tactile sensing. Our research introduces Coil-Tac, which is a soft transduction mechanism based on capacitance changes due to the movement of conductive liquid in a conductive helical coil. We will develop a numerical model for the mechanism based on finite difference methods for arbitrary implementation of the mechanism for purposes beyond those that we demonstrate here. Coupling the mechanism to a soft membrane serves as an example of how the mechanism can be used as part of a tactile sensor. The capacitance between two conductor plates changes as the conductors move or change shape. Coil-Tac uses conductive liquid metal for one of the conductors, meaning that any measured change in capacitance over Coil-Tac can be attributed to the liquid metal being deformed. Here the liquid metal is confined to a cylindrical tube so that its deformation is axial, as in the animation. Our work is primarily concerned with using a helical wire coil. However, as we move the pitch of the coil between its two extremes, we approach two important symmetrical configurations: parallel wire and concentric cylinders. These are analytically solvable due to their high symmetry and so provide ground truth configurations for our numerical approximation to be evaluated against. We use finite difference methods with Laplacian smoothing to approximate the electric field between capacitor plates and Gauss's law to calculate the resulting charge over the surface of the liquid metal in Coil-Tac. This modeling captures the fringing effect, where there is a significant increase in capacitance over a small region at the tip of the liquid metal, where charges can accumulate in a small area. This is visible in the animation of the electric field as a blue drop at the center of the area. The numerical model agrees with the analytical methods to within a few percent and interpolates between the cylindrical and parallel configurations as expected. With our numerical model agreeing well with the analytical solution, we synthesized our three configurations and tested them in lab conditions. We drove our liquid metal axially in 5mm increments up to 35mm. The numerical model gave capacitance predictions based on the position of the liquid metal that tightly agreed with what we experimentally observed. A silicone tactile sensor was synthesized with liquid metal embedded under its surface to use Coil-Tac as its sensory mechanism. It's able to sense small and fast tactile cues when operated by hand. Coil-Tac can be accurately modeled in a new configuration with a sensitivity tailored to a new specific purpose. It has been demonstrated to be simple to integrate into a soft sensor for fast and sensitive tactile data readout. Please see our paper for a more in-depth exploration of the mechanism. Thank you.